Good afternoon, everyone. Today, our group will present our music recommendation system process. Uh, I would like to introduce members in our group. First of all, I want to introduce my teammate Bùi Bá Phúc and Nguyễn Bá Nam. And lastly, I want to and I, Lưu Trọng Tơ. There are two parts in my presentation. The first is the identification of stakeholders and the benefits they derive from this system. The second is a description of the dataset we use and the processing steps we apply before model training. Let's get started. Our system involves three primary stakeholder groups, each with a distinct role and a clear set of benefits. The first group is end user, the listener. They interact with the platform daily and benefit from personalized music discovery, seamless continuous playback, and a feedback mechanism through client dislike that improve their experience over time. The second group is data scientists. They benefit from risk behavioral loss, including late duration, clients, and deadline, as well as a modular, scalable ML pipeline that allows them to interact on models independently at each stage. The third group is project manager. Their primary benefit is helping CTR click-through rate at a quantifiable KPI to governance release, measure business impact, and align organizational priorities. Importantly, the three groups from a reinforcing feedback loop and user-generated data. Data scientists improve models and better model price CTR and higher CTR translate directly into business values. Let me go a bit deeper into the country's benefit for each group. For end users, the home-based survey curates recommendation without any manual searching. The next song feature use content-based similarity to ensure uninterrupted playback. The line and dislike signal feed directly back into recommendation engine, creating a personalized love quiz that improves with every interaction. For data scientists, the system log run interaction events, play duration, lies, and decline, providing both implicit and explicit signal for training. The pipeline is designed in three modular stages: candidate generation, ranking, and serving, so each step can be improved independently. All key metrics are persisted in Postgres SQL, enabling fully reproducible offline evaluation. For project manager Cheetah, it tracks separately per recommendation survey home by per nation, allowing them to identify which survey drive stronger engagement. Cheetah trained across model versions provide objective data-driven criteria for release, approval, or feedback, and improvements in Cheetah directly correlate with lower churn and higher subscription retention. Now, for the data side, we use two datasets. The first is music is for .csv, a catalog with 1,500 songs with 18 fields. It covers 15 genres, each with exactly 100 songs. The second is user listening history. with around 4,600 interaction records linked with more than 30 users to nearly 900 unit tracks. Now let's move to demo.
Hello teacher, my name is Nguyễn Ba Nam and I will talk about the feature next song recommendations in our system. In this feature, we use content-based filtering, recommending songs based on the properties of the song themselves, without needing to know what other users listen to. Specifically, we use KNN to find songs that are closest in terms of audio characteristics. Each song is represented by 5 audio features. The first one is danceability, indicates how suitable the song is for dancing. The second one is energy, intensity, and perceived power. The third one is speed of the track. The third one is tempo, representing speed of the track in BPM. Balance, musical positiveness or negativity. And the last one is acoustic, how acoustic the instruments are. Each song becomes a point in 5-dimensional space. The closer two points are, the more similar the songs. But there is a problem. Tempo ranges from 90 to 180, while danceability is only a range from 0 to 1. If we compute distance directly, tempo would completely dominate the result. So our solution that we use min-max scaler normalize all features to the same 0 to 1 range before feeding them into the model. This ensures every feature contributes equally to the distance calculation. We don't use Euclidean distance, we use cosine similarity. Cosine measures the angle between two vectors. It cares about direction, not magnitude. For example, two songs that are both high energy, danceable, and upbeat, even with different tempos, they can still be very similar in the feel. Cosine captures that better than draw distance. Here is our demo notebook. We have 5 songs: Blinding Lights, Levitating, Someone Like You, Shape of You, and Believer. After scaling the features and training KNN with metric cosine, we call the function recommend songs and pass the song name into the function. The results show that Believer and Levitating come up first. Both have high energy and strong danceability, very close to Blinding Lights in audio space. Meanwhile, Someone Like You acoustic, slow, melancholic ends up that furthest way away. In the real system, the KNN recommender class in this file load all songs from the database, fits the KNN model once, and cache it in memory. When a user is playing a song, the API goes similar with the song ID and returns the top 6 most similar tracks in milliseconds. So to summarize, the audio features describe the sonic content of each song, min-max scalar balance all features on equal footing, and KNN plus cosine finds the nearest neighbors in feature space. Simple, effective, and requires no user history.
Good morning, everyone. Today, I will present training step for building a music recommendation system, focusing especially on homepage recommendation. The goal of this session is to recommend a ranked list of songs that a user is likely to listen to. This is different from the next song of the representation, where we focus on a next song recommendation using the content-based approach, which we will present later. For this experiment, I use a Kaggle music listening dataset Unfortunately, this dataset does not include explicit slide behavior. Because of this limitation, I use place counts and implicit feedback. In other words, if a user plays a song, we treat that a positive signal. Higher place counts mean stronger interest. But we should remember that this is only approximation of the user reference. First, we lost and merged the user's histories with music but then metadata. Is it we downloading the data from our database and put it in a CSV file. And this is final structure of our CSV file. It's including track ID, user ID, and play count. Next, I filter the data sets focus on active user and popular tracks to help make the training data more stable and reduces noise from user and song with too few interaction. After filtering, the data sets contain about 803 users, around 2,000 songs, and around 74,000 ranking. This means 1,000 of the interaction with our system, and we split the data set of 80 and 30, 80% for training and 20% for testing. And we also construct the user's item metric. So the metric is how the first dimension is 803 and the second dimension is 2,157. And we figure out that the densities of the data set around 3% is very spare data set because of the natives of our data. So for the baseline model, I tested 3 approaches. First, the baseline user-space collaboration filtering. This models find the user with similar listening behaviors and recommend songs based on the similar user listen to. The second baseline use is item-based collaboration filtering. Internet compare users, the model compare songs and recommend songs similar to the ones users has already played. The third baseline is truncated SPD, which is the metric factorization method. It's learn hidden user and item factors from the user item interact metric. The baseline useful because there's key other comparison points and collaborative filtering is simple and interpretable, while SPD uses stronger latent factors benchmark. The main selected models is 2 towers model trained on BR loss. So this is the item-based collaboration filtering. This is users-based collaboration filtering. And this is SVD's approach. So we put it in the comparison with our approach. For the main model, we have 2 separate towers. So let me scroll down to the architectures of the 2 towers architecture. So here, as you can see, one tower learn the user representation, and another tower learn the track or song representation. The user representation use user's ID embedding and the user activity features, while the item tower use track ID embedding. The music metadata such as general features. The model then compare the user and item vector using a dot product score. So you can see here we use after we do some projection, passing the data from the embedding. So we do the dot products, final dot product for the final score. Okay. For the training, I use a Bayesian personalized ranking or BBR. Instead of predicting exactly like how BBR learned a ranking reference for each user, the model trained to score a positive song higher than a negative song. This is more suitable for whole space recommendation because the goal is not only predict the number, but to rank the best song on the top. So this is a normal training flow of the deep learning model. And we use some, after we training around 10 epochs. So this is the results. So this is not a final evaluation. So we use the precision recall NDCG for the evaluation. So let's looking at the results. So here is the final results. The results showing the two towers is not only not the best for the Bruce mean square error or mean absolute error. In fact, the error is higher than collaborative filtering baseline, but it's expected because the model is optimized for ranking, not exactly the play count prediction. When we look at the ranking metric, so I have the visualization here. The results show that two towers model did not only the best for the recall resistance, but also the NDCG both at K equal 5, 10, and 20. This means the two towers model is best for placing relevant song near the top of recommendation list, which is exactly what we need to homepage recommendation. So usually we also have the ranking model like at the final step to further ranking, but for the time limitation, we don't have the time to implement this. So this is only the first phase that generate the candidate for our recommendation engine. So, so the key conclusion is for this experiment, the two towers BBR is selected as the main model because it is given the best ranking performance, even though the data set lacking of implicit lie or disline feedback. Using play counts and implicit feedback allows us to build practical recommendation pipeline. So next, I'm going to demo with you about the our backend and our system to manage how we're going to deploy our system. Hello, guys. Welcome back. I'm going to talk about our application and demo how we are going to deploy our strength model into our real world system. So in this case, I just build an application, a web application for our music service. So as you can see here, we have the home space, and in the home space, we have a list of recommended song to the user. So this is only available for the local user. So for the backend side, so this is how it looks like. So it's very simple. We connect with the only two sets of API, and the more important sets of API is the recommendation API. So in our application, we divide into two different kind of recommendation. One is the collaboration based filtering, which is used in the home page, and the content-based recommendation we use for the next song. And also we design the way to collect the data and to build our application feedback. So every time the user interact with our system, we want to send the data back to our system. Let's go to the database. So how the database look like? So this is just a sample of our database. So we have a list of the songs, and we have the user data tables, and we have the analytic event, which is the data we collect for the feedback loop that the user interact with our system, and we're going to use this database for training and retrain the model after the model is deployed into our system. So the next question is how we're going to manage the models. So for the managing the model, we have the MLflow. This is the service that we upload and manage the training and monitor the performance of the models. So as you can see here, we have two towers model, and I just talked in the collab with the notebook. And after we train the model, we upload the model into MLflow and store it into H3. And when the API start up, we download the model from the MLflow and do the inference. So we also do the placeholder for the XGBoost ranker. We don't talk about it in the main report and our presentation because this is a placeholder for the next step for further ranking the candidate for a better performance. But because of time limitation, we don't have time to talk about this one. Okay, and next, how are we going to use this model? So after we, as you know that if we using the SVD or translate the item user metric into a lower dimensional metric, we don't always use the deep learning model. We always got the user vector, the item vector. But the question is how we're going to deploy this in the real world application because the size vector are very big in a real application. So to do the cross dot product between the query and the songs, the song vector is a very expensive computation. So we did a benchmark on the different kind of technique to actually store and manage the data. So as you can see here, we do an experiment on different kinds of vector search, and it's also known as ANN, which is an approximate neighborhood. So you can see here that this is some really popular CPU and GPU vector search, and this is the latest HNSN. This is the latest algorithm is popularly used in many vector search engine, and also very popular. So as you can see here, between a trade-off between the average query time and the cost. So, and also we could also consider the recall at K of the query. So as you can see here, this algorithm got the best between the balance between the performance and the recall. So in our database, we're using the vector search in our database. So this database is actually the Postgre in the backend. In the Postgre in the backend, we also already support the different kind of indexing based on the vector. So as you can see here, so on the song here, the backing vector here. So when we query the song list in Postgre, we use these vectors and use the Postgre plugin to actually doing a search based on the algorithm that we just talked about. That's it.